Good morning, everybody. Here we are again with another seminar at the Instituto Astrofísica de Andalucía, in Granada, in Spain. And today we will have the talk by Sara Cazzoli, and she will talk about the unexplored outflows in nearby low luminosity AGNs, the case of NGC 1052. Sara Cazzoli has a degree from the University di Bologna in Italy and a PhD in astrophysics from the Universidad Autónoma de Madrid. She did her PhD thesis doing a search for neutral gas superwinds in nearby luminous galaxy with strong star formation at the Centro de Astrobiología in CSIC, Madrid, in collaboration with the Galaxy Evolution Group of the University of Cambridge. She is currently a postdoctoral research in the Severo Ochoa project here at the IAA in Granada. Her line of research is galaxy evolution with a special focus on active galaxies through the analysis of data cubes obtained with the integral field spectroscopy technique. She is co-author of 29 specialized articles in Q1 journals like Astronomy, Astrophysics, and Nature, and with plus over 400 total citations. She has participated in a specific evaluation committee, master and PhD thesis, and is co-supervisor of a PhD thesis. Her teaching activities include courses for the University of Andalucía in Murcia, as well as data management workshops. She is dedicated to science outreach also and promotion of the role of women in science since 2016. So thank you very much, Sara, for this talk, and the floor is yours.
Good morning, everybody. Thanks, René, for the presentation. It's a pleasure to share with you our recent work about unexplored outflow and specifically the case of NGC 1052. So perhaps to some of you...
Sara, sorry, you need to share the screen.
Oops. Sorry. Emotion. Here we are.
Yeah.
Okay.
Perfect.
Can I start?
Yep.
Okay. Hello again. It's a pleasure to share with you our recent results about unexplored outflow and specifically the case of NGC 1052. Perhaps some of you raised some eyebrows reading the word unexplored outflow together in the title of the talk. Indeed, outflows, at least the outflow phenomena, should ring a bell to many of you, actually a big bell. Indeed, in the latest 20 years, outflows has been widely explored. You can check this by doing a simple search in IDS with outflow in the title, with the referred publication and in the field of galaxy, and you will find more than 1,500 papers. And this is a lower limit because sometimes the outflows are called galactic winds in starburst galaxy. So thanks to this work, we saw many manifestations of the outflow phenomenon in nearby galaxy and active galaxies, such as M82 and the Circinus galaxies, and outflows are found to be common also in the more distant universe. Here we have the case of the Teacup galaxy. Overall, outflows are a common phenomenon. It is important to keep in mind that also our galaxy hosts a nice outflow called Fermi e Rosetta bubble. Outflows are made up by a number of phases: X-ray emitting plasma, ionized gas, neutral gas, and molecular gas, for saying some of the phases. And spectroscopically, these phases can be probed thanks to both emission and absorption line. In the optical range, we have access to the warm ionized gas thanks to Balmer line and other lines such as oxygen 1 and sulfur 2, and also to neutral gas thanks to the sodium absorption doublet. At longer wavelength, we can probe the molecular gas thanks to the CO line, for example. Today I will focus mostly in outflows in active galaxy. A quick reminder, galaxy host a supermassive black hole at its center, but only less than 10% can be called as active. Active galaxy host and active galactic nuclei are the center, and the different elements of this AGN are summarized here. So in the very center, there is a supermassive black hole. It is surrounded by an accretion disk. And then at larger radius, there is a region of clouds moving very fast called broadline region. And all these elements are enclosed within the dusty obscuring torus. At even larger distance from the supermassive black hole, there is the narrow line region and also the radio jet. Radio jet may propagate it either on millisecond or second scale, being small jets, but also can reach megaparsec scale and much farther than the extension of the galaxy. There is different AGN families, mainly that can be differentiated between supermassive black hole properties, radio emission, accretion, and orientation. Some of them are quasar, Cipher, blazar, BLAC, and I just want to mention that type 2 AGN are seen through the dusty obscuring torus, while type 1 AGN are seen in an intermediate line of sight that is not crossing neither the torus, neither the jet. In this type 1 AGN, we can access at the innermost region of the AGN close to the supermassive black hole. Outflow have a central role in galaxy evolution through feedback effects. And these feedback effects come in different flavors. These different flavors are summarized here in this picture by Usmer and Harrison 2008. And in particular, outflows in active galaxy can be radiatively driven by the AGN or mechanical driven by the jet. And they can provide both either or both positive, negative feedback or gas recycling. I will go briefly, I will mention these three different kinds of feedback. The negative feedback basically consisting in the gas removal and heating. This negative feedback can regulate both nuclear activity, star formation and AGN activity, as well as the mass growth. In the past, this negative feedback has been widely explored, and it is often invoked to explain the discrepancy between the galaxy mass function and the mass spectrum from simulation. The outflow feedback from supernova-driven outflow is more relevant at low masses, while for more massive galaxy, the AGN feedback and AGN outflows are more relevant. ¿Qué pasa? Sorry, but the pointing is not working. No. ¿Qué pasa? Ahora. The other kind of feedback is the positive feedback that has been only recently proposed, and basically consists in the possibility of outflow to undergo a vigorous star formation within the outflow. This kind of feedback has been studied through thanks to optical diagnostic diagram shown here on the top. And these diagrams are used to discriminate between the different ionization mechanisms, so star formation and AGN ionization, being both either Seyfert-like or Liner-like. Another way to explore this positive feedback is to compare the trajectory of the gas versus that of the stars. The gas recycling basically is the action of galactic fountains. The gas is ejected from the central region, but the velocity and the energy are not enough to escape the potential well of the host galaxy, so the gas is raining back onto the galaxy disk, being fresh fuel for star formation at later times. So summarizing, we saw outflows in different galaxy time and through cosmic time. We now know that this gas in the outflow is multi-phase with different temperature and density. We have three main power sources: star formation, AGN, and the radio jet from the AGN. And these outflows are able to provide different kind of feedback. All this aspect has been studied thanks to data and simulation. Some of these works were devoted to explore, to find the possible scaling relation between the outflows and the host properties. An example is this plot from Fiore et al. 2017, and they did a compilation of the known cases of molecular ionized and X-ray winds and tried to look for some scaling relation between the outflow properties and that of the host. In this plot, the mass outflow rate is plotted against the AGN bolometric luminosity. And on the one hand, we can see that the sample of the range of AGN luminosity is well sampled with from 10 to the 43 to 10 to the 48 erg per second. But on the other hand, we can see that the low luminosity range is completely unexplored. And this is the reason we found of the word unexplored to get the outflow in the title of my talk. Our group here at IAA devoted some effort to study outflows in low luminosity AGN. Some works has been already published and some are ongoing. So among low luminosity AGN, we are mostly interested in low ionization nuclear emission line region, also called the LINERs. These AGN has low X-ray luminosity and a peculiar optical spectrum. Here, the spectrum of the LINER NGC 1052 is compared to that of a more luminous AGN, the Cipher Galaxy NGC 1358. The peculiarity is that the LINER optical spectra show a bright low ionization line, such as oxygen 1, and faint high ionization line, such as oxygen 3. In the past, LINERs were also at the center of a debate. Indeed, their dominant mechanism, their dominant ionization mechanism was debated. There were three different scenarios: AGN, post-AGB stars, or shocks. All these mechanisms were studied thanks to optical diagnostic diagram. We saw an example also earlier. And for what about our study, we are sure that the dominant ionization mechanism in the AGN, as all the targets were selected at X-ray. So why study outflows in LINERs among the low luminosity AGN population? They are thought to be the most numerous AGN population in the local universe. So it is important to study the outflow phenomenon in this large AGN population. They are thought to bridge the gap between the normal and active galaxy, and moreover, outflows seem to be common in LINERs. We recently obtained an atlas of 70 LINERs we studied the H-alpha emission thanks to HST archival data and ALPHOSC data from the North Optical Telescope. And following Massegosa et al. 2011, we described the H-alpha emission as the sum of an unresolved point source plus an extended emission. This extended emission can be diffuse, resulting in a core morphology, as the case of NGC 2787, or can show spiral arm and star-forming ring, resulting in a disky classification, as the case of NGC 3226. These extended emissions can show the nice morphology of bubbles and bicones, such as the case of NGC 4438, and this would result in an outflow classification. In this sample of 70 LINERs, we found a detection rate of 70 LINERs. We found a detection rate of 32% of outflow, and this percentage, the detection rate, can rise up to 50% if we include spectroscopy detections. So we also study outflow using spectroscopy with SLIT spectroscopy in a smaller sample. In this case, were 31 liners, both type 1 and type 2 liners. We use the archival data from HST again, and also ground-based data from Twin at Calararto Observatory and the Palomar survey. So we try to identify outflows as broad and blue shifting component in emission line, as done widely in literature, thanks to this diagram, which is the velocity dispersion plot, and outflows were considered with large velocity dispersion and blue shifted velocity. The outflow rate for this sample vary from 20% in the case of type 2 liners to the 40% in type 1 liners. So outflows are indeed common in AGN-LINERs. These outflows are extended dotted, and the different detection rate we saw in this work may be affected, for example, by the orientation of the slit. Indeed, if the slit is not placed correctly, we can actually not capture the outflow as a broad and blue shifted component, and so we can actually have different detection rate. Moreover, outflows as a standard objective, their properties may vary along the bubble. So we can see velocity gradient, difference in velocity dispersion, and also in electron density. So SLIT spectroscopy is an efficient way to have a first guess of the presence of the outflow, but the most efficient way to obtain a description of outflows and their properties is integral field spectroscopy. Indeed, IFS data are cubes with 2 spatial and 1 spectral dimension. Basically, for each pixel of in your field of view, you have an entire spectrum to explore. We are mostly interested in studying the optical band, as we have access at 2 gas phases of the outflow, and we are interested in using MEGARA at GTC, integral field unit, and MUSE at VLT. From this survey, we selected a sample of the best case of outflow, and we follow up this sort with MEGARA at GTC, and we obtained data for 11 targets, and we are now analyzing all the data. Today I will present with the case of NGC 1052. We started our exploration of outflows in liners with this case for 2 main reasons. On the one hand, we were able to obtain both MUSE and MEGARA data that nicely complement each other in terms of spectral resolution, spatial resolution, and the field of view covered, but also because NGC 1052 has been considered as the prototypical liner. NGC 1052 is a nearby object, only 23 megaparsec away. It is a type 1 AGN, so type 1.9 more exactly. So we have access to the broadline region, to the innermost region of the AGN. This AGN is hosted by an early type galaxy, either elliptical or lenticular, depending on the author. But in any case, there is a late type galaxy with a low level of star formation rate. NGC 1052 in the center hosts a radio jet. The direction is shown here in pink, and this radio jet is detected on milliarc second or second scale, and is oriented is not oriented as the photometric axis, shown here in green. Here the optical continuum emission map from both MUSE and MEGARA data. Actually, for MUSE, we were able to cover nearly all the optical emission thanks to a mosaic. And it has to be said that for this case, there are 4 different integral field spectroscopy studies, but these were limited either in spatial resolution, wavelength coverage, or field of view covered. More specifically, Dopit et al. In 2015 covered the 38 arcsecond times 25 arcsecond at 1.3 spatial resolution. So this is a field of view covered by Dopita, and the resolution is worse than MEGARA and MUSE. Sugai et al. 2005 studied only the innermost 3 arcsecond times 3 arcsecond region of this object at very high spatial resolution, but analyzing only the oxygen 3 line. The works by Dameran 2019 and 2020 analyzed a even smaller field of view than Sugai at a resolution comparable with MUSE. So thanks to our data set, we can cover the near all the optical continuum emission of NGC 1052, a high spectral resolution and spatial resolution. To start, we are mainly interested in study gas emission. To do so, to well characterize the gas properties, we have to take into account possible possibly strong stellar absorption that affect mostly Balmer lines such as H-alpha and H-beta and the sodium doublet. To do so, we modeled the stellar component in NGC 1052 in both datasets on spaxel by spaxel basis, and here you can see 2 examples of the fit. In the top panel, the observed spectrum is in black, the model is in red, in gray the reason we did not consider to their fit, and below the subtraction. So this one is a purely ISM spectrum we want to study. This stellar component analysis has been done thanks to 3 different tools: GIST, penalizer pixel fitting method, and Voronoi binning. These tools also allow to study the different moments of the line of sight velocity distribution. As we were mainly interested in gas, we study only the first 2 moments of this line of sight velocity distribution, and these are velocity and velocity dispersion. So here the maps of the velocity field and the velocity dispersion map for MUSE and MEGARA. For the velocity field, we see the typical pattern of a rotating disk, the so-called spider pattern, and this disk has large peak-to-peak velocity of more than about 170 km per second. The velocity dispersion map is centrally peaked, as expected in a case of rotating disk, with large central velocity of about 200 km per second and average velocity dispersion of about 145 km per second. Thanks to this kinematic information, we were able to study the rotational support of this disk by using the dynamical ratio, the V over sigma ratio. This value is found to be 1.2 in the case of NGC 1052, indicating that the disk is dynamically hot, so the random motion component is important in the kinematics and dynamic of this disk. Take into account both kinematics and dynamics and compare this value with literature, we consider that the stellar component in NGC 1052 is more similar to that of lenticular galaxy rather than an elliptical galaxy. Then, with the pure ISM spectrum, we modeled emission lines with up to 4 kinematic components using Gaussian function. Here, example for both MUSE and MEGARA data. These components are listed here and can be discriminated using their width. So the primary component was the narrowest, and then the other component was broader and broader and broader. So of this component, 3 components were used to model all emission lines, so oxygen 1, sulfur 2, nitro 2, and oxygen 3, and Balmer lines. And of these 3 components, the broadest one with velocity dispersion larger than 300 km per second is partially unresolved, so is extended only in the central region affected by the point spread function, the PSF. Due to this, we didn't do extensive analysis of this component. The very broad component has been studied, has been found to be necessary only to model the H-alpha emission, and is very broad with large full width alpha maximum, more than 2,000 km per second. Also, this component were spatially unresolved, but due to this large full width alpha maximum, and that is detected only in H-alpha, we consider that this component is from the broadline region of the AGN. The other two components, the narrowest and the second one, broader, with velocity dispersion generally larger than 150 km per second, are the two components that were found to be spatially resolved, and we focused our analysis on these two components. From our modeling, we generate velocity, velocity dispersion, and flux map, as well as other maps, such as line ratio and electron density map. So we found, and then we compare MUSE and MEGARA data. We found that the results in terms of number of components and the general behavior of the maps are in agreement. So we are in agreement. So today I will mostly focus on MUSE data, as we were able to sample the ionized gas up to the largest radio. And today I'm going to show you the maps of from the modeling of the oxygen-3 line. So for who is not familiar with integral field spectroscopy, and also for people that work every day with this kind of data, the maps were a little bit complex and difficult to understand. So what I'm going to do now is to walk you through what you are going to see in the maps with a simple scheme. More specifically, you are going to see MUSE map in 3 different field of view. The largest one, which is basically the field of view of the mosaic, a reduced field of view, and the smallest field of view that match that of MEGARA. And these 3 field of views were selected to enhance, to show better the different features. As reference, on the bottom left, the size of the point space function, the PSF. As well, we mark the direction of the photometric axis and the radio jet direction. For the narrow component, most part of the emission is detected along the polar direction, which is perpendicular to the photometric axis. Part of these emissions show a large velocity dispersion with a peculiar butterfly morphology, mostly along this direction, which is the same as that of the photometric axis. For the second component, is not aligned with neither of 2 directions, but it is aligned with the radio jets in this along this direction shown in pink. I'm aware that with this scheme, I did a little bit of spoiler what I are going to see, but I hope you appreciate the maps and also this premise, and I hope this scheme helps you to read the map. So here are the maps of velocity, velocity dispersion, and flux for the narrow component, top and middle panel, and for the second component in the lower panel. And here are the different scheme I've shown to you. So let's see what are the different features of these different components. So the narrow components show this extended emission up to 30 arcseconds that are about 3 kiloparsec in the polar direction with these nice blue and red sizes, and also show this central region with large velocity dispersion marked with contours here and here that we will call butterfly region or butterfly emission. Along the polar direction, velocity are up to 250 km per second, and the velocity dispersion is low, of about 50% kilometer on average. In the butterfly region, the kinematic is a bit more extreme, with velocity up to 300 km per second and large velocity dispersion. To isolate this butterfly region, we consider the limit of 90 kilometers per second. And this limit has been obtained by taking the 2 sigma above the average of the velocity dispersion in the polar direction where there is no peculiar feature. Then from the line ratio of sulfur to line, we calculated the electronic density, which is lower than 100 centimeters to the -3. And the BPT line ratio indicate a liner-like ionization mechanism. We will see a little bit later some more information about these BPTs. For the second component, it is extended up to 7.2 arc-second of about 800 parsec with this naive bipolar and symmetric morphology, and this emission is oriented similarly to the radio jet. Here the kinematics is indeed more extreme, with velocity up to 650 kilometers per second and large velocity dispersion. Again, we calculate the line ratio. In this case, the gas is more dense with electronic density larger than 100 centimeters to the -3. And again, we found that BPT ratio indicate a liner-like ionization mechanism. So here are the BPTs with the different line ratio. And these are 3 set of BPT. We isolate polar emission, the central butterfly region, and the second component. To analyze these BPTs, as a first step, we consider the dividing line by Kaufman et al. 2003 and Kivli et al. 2006 that are able to well discriminate between ionization from H2 regions, so star formation, and AGN, being either Seifert or liner-like. We also consider the criterion by Filipenko et al. 1992 that for large values of oxygen 1 over H alpha, the object can be classified as oxygen 1 strong, so genuine AGNs. So taking into account all of these dividing line, we found that generally the ionization mechanism is liner-like, so there is no contribution of star formation, and all the line ratio indicate oxygen 1 object or point. We also tested another possible scenario. So we used the prediction for post-AGB stars using the model by Binet et al. 1994, marked in pink as a pink boxes in these diagrams, but these predictions are not able to reproduce the observed line ratio in NGC 1052. So this scenario was excluded. Also, we considered shocks model of by Groves et al. 2004, but with differences between the narrow component and the second component. So the models that best reproduce the observed line ratio in NGC 1052 for the narrow component are shocks plus precursor models. So the gas is ionizing itself with both elements. We considered the model with solar metallicity and the electronic density and the velocity we measure in our data cube. And these are the grid shown here in blue and red. And these shocks model are able to reproduce line ratio in at least 2 of these 3 BPT diagrams. For the second component, we used only shocks model, so the gas is collisionally ionized. Again, we consider solar metallicity and the values of electron density and velocity we measured in our map. And again, we can see that nitrogen 2 over H alpha and oxygen 2 over H alpha diagrams are able, the shocks model in these diagrams are able to produce nearly all the observed line ratio. So taking into account the dividing line and shocks model, we consider that the ionized gas probed by the narrow and the second component is ionized by a mixture of AGN and shocks. So what we with all these results in hand, we try to make sense of what we are going to doing. So now I'm going to show you our proposed scenario for the gas in NGC 1050, ionized gas in NGC 1052. So as a reminder, we saw for this object a nice stellar rotation with blue and red sides, with a kinematic axis well aligned with the major photometric axis. We saw that part of the gas emission is extended in the polar direction and part in the radio jet direction. More specifically, we consider that the second component that is probing high density turbulent gas with extreme kinematics being collisionally ionised is probing the outflow in NGC 1052. This outflows is propagating in a cocoon of gas with low density and low turbulence, which is probed by this nice butterfly region, butterfly emission probed by the primary component. This interaction between with the gas and the radio jet and the cocoon is triggering the expansion of bubbles extended on kiloparsec scale with clear blue and red velocity, with again low density gas, less turbulent gas. This is a scenario we proposed, and then we tested what is the possible power, what is powering the outflow in NGC 1052. We consider all the three possibilities. Star formation in NGC 1052 is too low to power the outflow with energy of 2.2 times 10 to 58 erg. This energy of the outflow has been calculated following Morganti 2021 and Venturi et al. 2021, and we consider that star formation is not excluded. So we calculated we compared this energy of the outflow with the AGN power and also with the energy of the radio jet, which is 1.3 times 10 to the 58 erg. And this has been calculated following Mukherjee 2018. So we consider that the most likely power source of the outflow is the radio jet due to the energy, because the jet is able to power this outflow, the orientation. This second component is aligned with the radio jet, and also the shocks models we used. Without precursors, the gas is collisionally ionized, and this could be due to the passage of the jet. However, we didn't rule out a possible AGN contribution to this to the power source, to the energy for launching the outflow, as also the AGN is able to power this outflow. Then we estimated the typical parameter used in literature to estimate the feedback, so the mass of the outflow, the mass outflow rate, and the energy rate, and compare this value with the property of the host, finding that even if this outflow is not massive, so the mass of outflow rate, the mass of the outflow is low, and also the rate of energy and mass are low. So we consider that the feedback on the host by this outflow is weak. As a last step in our analysis, we studied the property of the neutral gas, looking for a possible counterpart of the ionized outflow. As a first step, we tried to again exploit MUSE data, and we calculate the equivalent width of the sodium absorption doublet. However, we found that this feature in MUSE data is weak, with equivalent width of about 1.2, 1.5 on average. So we prefer to use for this kind the part of analysis we prefer to exploit MEGARA data where the sodium doublet is observed at high signal to noise. Here the velocity dispersion and flux map from this sodium absorption. Here an example of the modeling. So for the neutral gas, we found that the gas is optically thick. The ratio between the two lines is of about 1, so indicating an optically thick gas. In the velocity field we can again recognize this nice spider pattern with blue and red size. But in this case, the velocity dispersion is not centrally peaked as in the case of, as expected for rotating disk. Actually, it peaks more or less here at 2.5 arc second eastward from the nucleus. And this peculiar morphology in velocity dispersion map does not have any counterpart in the flux map. So taking into account all the analysis of the maps, taking into account the result from this map, we interpreted the neutral gas as being originating in an irregular and slow rotating disk with a low peak-to-peak velocity less than 100 kilometers per second. Having said, we tried to do a tentative outflow detection. So we did similarly to what we did for the butterfly region. So we excluded the nuclear region. We take the average velocity dispersion outside the nucleus and take the 2 sigma above. This limit, with this approach, the limit in velocity dispersion is 245 kilometers per second, and the region of the map with larger velocity dispersion are marked here with this contour. So it's a very small region with a clumpy morphology with mild kinematics. So it's a tentative detection of the neutral gas, a possible neutral gas outflow in NGC 1052. And with this with these results, I'm finishing my talk. I summarize here the different takeaway messages about stellar component, the ionized component, the ionized outflow, and the neutral gas kinematic. The best is yet to come. We are exploring outflow in other low luminosity AGN, and I will be happy to take questions if any. Thank you very much.
Thank you very much, Sara, for this talk. And as you said, the talk is open for questions. For the participants in Zoom, please raise your hand. And Sara, you can take over the questions in the room. Questions?
So I think in the room, we're okay, right? Now, Martin.
Okay, we have 2 options. You can approach with the micro or you can repeat the question.
Okay, sorry for the question if this is very naive. I'm not expert in this field, you know, but how does it compare the scenario that you propose for this object to those that explain the outflow in more powerful AGN? And in particular, I mean, for both the different mechanisms that are producing the outflow, but also to me, it's very intriguing, but maybe you can explain it better. Why the misalignment between the whole kinematics, the whole dynamics of the galaxy and the jet?
Okay, so thanks, Martin, for the questions, and are not naive. We tried to compare our results, our scenario with literature, and there is some similarities and some differences. On the one hand, you cannot really compare outflow in a more luminosity AGN because the power source is completely different. And for example, if you have a powerful AGN, you can launch the outflow in different in different direction. Well, if a weaker outflow, maybe a weaker AGN, you have a privileged direction, looking for the path of last resistance, as seen, for example, in Eulers and starburst. And this for the AGN powering sources. For the radiojet, the radiojet outflow connection has been recently proposed. It's not well explored. Some of the work proposed that this enhancement in turbulence is aligned along the radiojet. Some other work proposed that this enhancement in turbulence is perpendicular to the radiojet. So perhaps there are two possible scenarios, and it depends mostly on the radiojet and the distribution, perhaps of the ISM surrounding the jet. So we are still investigating it, but we looked for some analogies and difference, looking to interpret this cocoon of gas, because at the beginning was really intriguing. And for the misalignment between the gas and stars, we actually explored two main possibilities. One is the emerger. Emerger can actually create this misalignment if it is strong, but we didn't see any evidence of merger. So we just, there is other possibility, and we try to investigate if these polar emissions are not actually bubbles, but a rotating disk, but the velocity, but the kinematics, the overall kinematic was not comparable with the kinematic disk, with the rotating disk. So we tried to, we did these two approaches, and at the end, when we found this second component, we tried to understand the mechanism and of this large turbulence emission. We thought that the most probably relation or explanation for this bubble in this polar direction was this interaction between the jet and the ISM. This is what the best we can do, also because in liner like Galaxy, they are not, there is not much gas. So we actually found a peculiar case. And during the, I mean, I have some doubt if it is truly the prototypical liner. So, but yes, we started the exploration with this because on the, it's thought to be one of the best cases, and we have both data. So we can compare, and we could check if the kinematic component truly exists in both data sets or depend on spatial resolution, spectral resolution. So we are pretty sure about our results. And but yes, yeah, there are some intriguing questions that can be followed up at other wavelength or just doing other kind of analysis. See? More questions?
Here online we have Montserrat. Go on, please.
Hello, Sara. It's Monse
Hola,
here.
hello.
Yeah, I have a question regarding the spectral resolution between, well, first, thanks for the seminar, which I have enjoyed a lot, of course. My question is whether you find any advantage on using the spectral resolution by MEGARA, which is significantly higher than MUSE, to study this kind of outflows. So do you think it's an advantage?
Of course, a higher spectral resolution is an advantage. So we did a nice comparison between two results. We did a parallel line modeling. So for example, we tried different models for emission lines, because some previous work found that oxygen 1 line and sulfur 2 line cannot, maybe not behaving in the same manner, in the same way between in-liners or in outflow. So what we did with MEGARA, for example, is to study this oxygen 1 and sulfur 2 line at higher spectral resolution, and then apply the results to that of MUSE. So we found actually some advantages, But at the end, we preferred to study these bubbles with MUSE because we can cover all the extension of the bubble. So we did the first run of modeling with MEGARA, exploiting all the spectral resolution, as best as we can, the spectral resolution, and then we applied all these results in MUSE data at higher spatial resolution and a larger field of view. So in this case, we did a lot of analysis with MUSE, but what we are seeing in with other galaxies in the sample with MEGARA data, we saw that actually the nice spectral resolution of MEGARA, that is the lowest available with MEGARA, is actually allow us to obtain to map different components that, for example, with other kind of data we cannot. So MEGARA is a very nice instrument, but for this case was a little bit limiting the analysis if we would base only in MEGARA data.
Okay.
I hope this answers your question.
Yes, thank you. Thank you.
Thank you, Monse. Another question for Sara? In the room, do you have more questions?
No, we're okay.
Okay, so seeing no more questions, we can close this talk. Thank you very much, Sara.
Thank you.
For this talk, for this seminar.
And sorry for the beginning that the technical problem.
Okay, I will close the recording now. Okay.